activity. But there is a lot of disadvantages. It's difficult to use because, you have a number of issues there. So it's not for continuous recordings. A lot of drift in this equipment. You need to recalibrate from time to time. It has a big disadvantage. It's extremely sensitive to all sorts of motion artifacts, and it's not that easy to deal with it. And of course, it has, as I said before, there's difficulty to measure the blood flow unless you use a contrast agent, because there are confounds. So it is not so easy to use technology. And of course, it is extremely slow. It's again related to this bolt signal. The time frame, the changes you can observe is in seconds in seconds level. So it's not very fast. You need to do a couple of those runs. So it's not very fast for BCI purposes. Indeed, it will be a very slow BCI communication. You have then in slide 48 some experimental setup. Of course, this is not for commercial purposes. It's much more compact than that. But of course, also the quality of the signals will be compromised. So this is the sort of setup, not easy technology. It's on slide 48. Why is it used? Well, in clinical environments, it is used for newborns or for premature born babies. Where on slide 49 you see, especially slide number 50, you see a premature baby, 26 weeks. This is a bit the edge of viability. If it's lower than 26, it's not going to survive. It will be, the organs are not to a sufficient extent, but to see if there is brain activity, you can do this with a simple NIRS electrode called optode, because it's optical. To see if there is brain activity, if there are changes in alpha rhythm and so on. If it's when sleeping, is it delta rhythm and so on. So to see some brain activity changes and so on, which are a good indicator that the brain is going to be okay. So in that sense, it has clinical use. This is a picture on slide 51. So there is a laser here that is sending that near-infrared light into the brain, and then you have a sensor that is picking up the reflected activity, and the difference is what is absorbed, right? So this is how it works. This is slide 52, some equipment that shows the oxygenated level and the deoxygenated level, the cytochrome level, and so on, until I don't know what it is. So this is a difficult technique to work with. In slide 53, I'm not going through that. You see a number of data acquisition thingies, what sort of technology and so on, what the major problems are when you use this kind of technique. And then on slide 54, there is a sort of overview of different techniques, invasive versus non-invasive. It gives you a bit of a picture. This is the invasive stuff, all right. So the single cell recording, where the electrodes goes into the brain. This is the multi-electrode, like the Utah array, going into the brain. But the scale is a bit weird. So the vertical scale is the spatial resolution that you can easily understand. But the horizontal scale is a time scale. And it's a bit weird because on the left side of the ellipsis is a bit the time resolution of the events you can pick up, and the right hand side of the ellipsis, if I understood it properly, is sort of how long you can record, something like that, how stable the signals are, something like that. So it's a bit of a weird scale. You see immediately that the invasive techniques are doing much better than the non-invasive ones in terms of the spatial resolution. You see MEG here, EEG, ERP refers to the EEG. This is the sort of spatial and time frame of EEG. You see MRI, fMRI we just discussed. PET we didn't discuss, but this is based on radioactive tracers, so it's something similar. You have glucose, sugar that goes to regions that are more active, and if that sugar is labeled with radioactive compound, then you can pick up the differences in the radioactivity in the brain as a matter of speaking, and this gives you an indication of differential activity in the brain. So this is the range and the resolution of PET. Then you have TMS, which we did not discuss because it's actually not much on recording. This is a stimulation technique, transcranial magnetic stimulation. So it's stimulating the brain rather than recording. So we didn't discuss it. And then you have naturally occurring lesions, which is a bit a euphemism for a stroke. When you have a bleeding or something like that in the brain, then there will probably be damage, permanent damage, or not permanent if it recovers. That's on the right-hand side of the ellipse. And the recovery can be over a process of much longer than that. It can be 60 days or so. Naturally occurring lesions. So it's a bit of a euphemism. Slide 22. Okay. So unfortunately, I have to flip through everything. So the question is to explain slide 22. I will try to do that. This technology is not very interesting. Okay, slide 22. Can you see my the student that posed the question? Can you see my cursor or not? Can you see the cursor on the right-hand side? Aha, you can't see the cursor. Okay. You have a Mac, I think. Okay. So on the right-hand side, you see the synapses. Axons are coming from the bottom, and they're connecting here on the top part, the apical part of the dendritic tree of the pyramidal neurons. And and these are excitatory synapses, so they give more activity, higher voltages inside, when you measure it inside the neuron. But outside the neuron, the polarity is reversed. Okay, what is a plus inside is a minus on the outside. Remember that. So on the bottom, on the apical, on the basal part of the neuron, so close to the cell body, you have all these pluses on the outside. So you have the minuses on the top and the pluses on the bottom. It's like a battery, okay? You know what a battery is, what you put in an electrical device. It has a plus and a minus polarity, so the minus is on top and the plus on the bottom. So if you put an electrode in that facility and this thing comes up, you see a negative deflection in your activity that you record with your EEG electrode, right? So you have a negative glitch, and the negative glitch is simply related to the polarity of the dipole. On the left-hand side, for the three neurons shown on the left, you have the opposite case. You have an excitatory synaptic input that is connecting more on the basal part of the neuron here. So you have excitatory, so pluses inside the neuron, but minuses outside the neuron. So this is the one part. And then you have these ion flows, right? And then you get on the top part of the dendritic tree the pluses on the outside, right? So you have again a battery. Pluses now on the top and the minuses on the bottom. So this forms a battery. And this battery, when it is activated, you see that the electrode on the scalp is recording a positive glitch, positive deflection in the amplitude. So is that clear now? Okay, so yeah, we still have like 5 minutes or so. I will try to mount then to upload that the next chapter, chapter 8, if that works. The imagined movement case, so chapter 8, so it's loading. So we are already pretty well halfway the course, so we're like 12 chapters. This means we are now chapter or lecture 8, so we are getting, like 1/3 still to cover. So everybody can see now lecture 8 being projected. So we are looking here at